And so we're going to go ahead and make an extra assumption for the pendulum problem that the angle is small. And small here again means usually about less than half a radian or so, which is about 30 degrees. Really, you want to get it into like the 10 degree or less range if you want like real, percent or less accuracy, but you're still within less than 5–10% if you get up to about 30 degrees. So we now have that this equation is approximately true. And now we have exactly the oscillatory equation. So I can go grab all the things that I already know. I notice by quickly solving this that I get an angular frequency, which I'm going to call omega p for the pendulum, which is the square root of g over L, so a different angular frequency than we had for the block on a spring. And I can write theta as a function of time as theta max, the initial angle that I pulled the pendulum to, times the cosine of omega t. I can also take some quick derivatives here and see what else I learn. And I notice here that I right away have a couple of omegas in the same problem. And there's a reason that I threw a subscript on the angular frequency of this guy, because I didn't want to confuse it with the angular velocity of the pendulum as it swings back and forth. So those are different omegas. That's the thing to watch. If I wanted to here, I could note that this stuff in front of the sine function now is going to be the maximum angular velocity of the pendulum, which is related to the maximum speed of the pendulum. And so I've got a nice relationship here that if I wanted to, I could write it in terms of velocity instead. So we've got a lot of power already just by making this simple small angle approximation. We can basically leverage all the stuff that we already did for oscillation.